Another important things, and we were extremely surprised about this, was that we were having a device with our collaborators. This was a work done in collaboration with ON Semiconductor, with Peter. So with some development, we were able to have device with a pretty decent current collapse at room temperature. Okay, so we are happy. Dynamic RDS-on is almost zero whenever we buy our device, so we were happy. Then we went to higher temperature. Same device, same bias condition, huge current collapse. Wow, this was something we did not expect, because in general, if you go to the silicon physics, and we take a silicon device with some traps, and you do measurement at higher temperature, you see much less trapping. Simply because the higher the temperature, the easier the electron escape from the traps. So in general, at certain time constant, you have a much less trapped electrons at higher temperature, because just the electrons are easier to escape. What happens here? We have a trapping that increases with the temperature. The reason for that is simple. In simple physics of trapping, you make a big assumption. The trapping time for electrons when it reaches nearby a traps is 0. Trapping time is 0. And when the electron is within the traps, to escape, it takes time. That is proportional to the activation energy. Who is the energy between the electrons level and the top of the trap hole, okay? So it's just the energy that electrons need to have to escape from the trap. But again, the assumption is 0 trapping time. Then what we did with our device, we just monitor not only the detrapping, but we monitor the trapping transient. Here I'm not monitoring the drain current, but this is the on resistance. Just also to stress on the dynamic RDS-on. You see that when we were doing our trapping state, so negative gate bias, relatively high VDS, and we monitor the dynamic RDS-on, you see RDS-on starting at the initial level, 1, this is the normalized. And then for some time, if we do at a relatively low temperature, after a long time, the on started to increase. This is 10 to the 3,000 seconds, 15, 20 minutes. If we follow this, maybe it takes days to reach the steady state. So it means the on increase because of charge trapping, but the trapping takes hours or days. It's not 0 trapping time at all. If we increase the temperature, we speed up the process. So at 140 degrees C, you see that the on increases much faster, but still requires time. And also, you see that the higher the temperature, we saturate it to higher level. Like if the higher the temperature, the higher the amount of electron that we are able to trap. This is a scenario completely different from any other kind of semiconductor we have seen until today, gallium arsenide, silicon, any structure. This was peculiar of gallium nitride, observed for the first time in this kind of structure. And then, of course, the detrapping, so the dynamic RDS-on, this is really tells you the dynamic RDS-on. At the initial stage, the RDS-on is high, and then little by little, the on goes down, but takes hours again. Takes a long time to recover. This is the other peculiarity. So trapping phenomena require a long time, up to hours or even more. Trapping time lower at higher temperature, this is reasonable. But the detrapping also requires a very long time. And this is something you have to take into account about this. Then this activation energy, where it comes from? Then we were struggled. Is this trapping happening at the surface of the device or at the buffer? So we developed a new technique, what we call the back bias, the back gating, okay? So instead of having the device bias in the typical condition that I show you, negative VGS, high VDS, okay? In this case, we have some electric field here, some electric field vertical. So we may suppose that if the trapping is in the back barrier here, most of the trapping are here. But if we do the back bias, so we put a 0 bias condition on the top and we just put a -25 in the back, Now electric field is all over here, so we are injecting a lot of electrons all over the substrate. And these are the two effects. You see, this is with the normal state, this is with the backgating. Clearly we see a much larger trapping here because yes, we are investing, we are considering or exploring much more area. Here the source is 0, the gate is just -8, so very little electric field here, no charge trapping. I'm not injecting any electron there. Electric field is so low that electrons are quiet. The only high field region is here, but here we have a high field region all over the device. And this is why we have even a bigger dynamic RDSON. With this, we really identified the problem was in the buffer. So after many other measurements, we clearly identified this condition. And at the end, with evolution working on the buffer, interacting with the material provider, the result was that we were able to get with last year with Peter in on-semi device with a 0 current collapse. This is just a 10%, 20%, up to 600 volts. Just to give you an idea, I put here this plot. This is dynamic RDSON, but this is not as in a scale much different from this. This is 60%. Here 60% is here, okay? So this is 0, this is 100%, 60% is here. So this is the device that we were measuring in 2012, 5 years ago, not 20, 5 years ago. Current collapse at 200 volts that were around 1,000%. With the evolution, the better quality of the material and so on, with many projects we have done, hypo-switch, A2 GaN and so on, we learn a lot of things, and today we have a device that has 0 current collapse at these high voltages. But this was a very big effort related to surface, to material properties, processing, field plating, treatment, chemical treatment of your device. It was really a big effort. This is also a plot I like to show. Peter did not show yesterday, but he developed a device at 1200 volts without current collapse. This REON, dynamic RDSON, up to 1200 volts. You see, it's flat. There is no changing in the REON at very high voltages. And what they did, they really improved the EPI. The three kind of device here are the device with different EPI, and device with the best EPI here present a much less dynamic RDSON, lower than 10%. So again, today for power device, the surface is somehow less controlled. You may easily control the surface and you can get no trapping at the surface. The biggest problem today is the buffer, is the GaN buffer, where with the compensation you have to work a lot for improving this. And this ends up my second part of my talk that was related to trapping. Now I would have another part of my talk that I will try to squeeze in 25 minutes because it is maybe a little longer. It is related to the problem with the reliability, what we really call degradation. So trapping is a temporary problem, but it is still a problem, okay? Because from the point of view of the application, trapping is a problem as big as reliability, in the sense that if I have a device with a large current collapse, it is unusable for my application. But it is not really a problem of degradation, of the device working, it degrades. Let's go to this field now. We go to see devices in which they show degradation. So this I sketch a cross-section of a typical gallium nitride devices. And what we did here some years ago, we published this paper, we were just identifying which are the different areas in which you may have degradation. You may have degradation at the gate edge because this interface can provide problem. We may have a problem at the ohmic contact. We may have problem of injecting electron at the passivation. We may have problem at the gate edge where there is a very high electric field. I show you at the beginning, electric field is peaked at the gate edge. And since these devices are sustaining very high electric field, the electric field strength is very strong, and you may have degradation problem there. And then we may have traps here. So here we are just sketching all the possible problems that we may have. I would not speak about gate degradation and ohmic contact. Yesterday, I believe Farid and also Peter, maybe Monday, spoke about that. What I'm going to show you was one peculiar degradation mechanism that we have seen in this device are the number one, the gate edge degradation. And number 4, what is a traps generation that we may have here. Because the high electric field, we may really have a strength of the field strong enough to damage the lattice, to create a defect, to create some real physical defect within the device. So the first degradation mechanism that was identified was this gate edge degradation. So what happens here? I mean, this was the work, pioneering work, I would say, from Del Alamo in 2008. They really showed this for the first time. They were taking a device, biasing in a reverse drain to gate condition. You see here, so we are giving negative gate bias with respect to the drain, having a high electric field, and during increasing this VDG, a certain time, he found what he called the critical voltage, at which the device, let's say, at 20 volts, started to have a large increase in the leakage current through the gate. Imagine that you want to use this device for power application at 600 volts. This is useless, because at 20 volts, I start already to see a degradation of the gate. At that time, we were not speaking of a power device. We were speaking of RF device, where the voltages were around, let's say, 20 to 50 volts. But this was extremely interesting. And then if you look, this is a work that we have done following this analysis. You see, we did a similar experiment. So we take the device, we did the stress, maybe the only change was that we put a source and drain connected together, negative gate to the stress to the gate, moving towards these curves until we see the critical voltage. And this is an electroluminescence measurement, the device before any damage, before the stress at 30 volt, no degradation. And then whenever we increase the gate bias and we started to see the increasing the leakage current, we started to see the appearance of the hotspot along the gate. So this is the same device during the stress at 30 volts, minus 30, minus 40, minus 50, and so on. And you see the appearance of many, many spots. So we are degrading the gate edge. So really, we are creating damage at the gate edge here. In fact, with some group that did some TEM analysis at the gate edge, they started to see this kind of guys, this crack. It always has been a debate if these cracks were there before the stress or after the stress, or if they have been generated during the stress, or if they were there before and activated after the stress. So this no one can tell you. But at the end, there was this kind of problem. A very nice experiment have done by the group of Palacios and also Del Alamo. They were taking the device. They make different kind of stress level. You see 15, 20, 42, 57, where they see the increasing of the leakage current. And then they took a device, they remove any metal. So here they remove the gate, they remove the metal, the ohmic contact. They see nothing on top of the aluminum gallium nitride. However, in the device stressed at 15 volts, they started to see some signs. So after the removal of the gate metal, they see these holes, and these holes became bigger and bigger as the stress was more severe. So what they've seen, it is again, during this VDG stress, we do have a kind of a real degradation, and we see a mechanical degradation of the gate edge. There was a lot of history to attribute to what. It was not easy, because also this kind of degradation was not observed from all the group in the world. There was some specific group working with a specific technology that were observing this. But they prove evidence that this was really the case. Oh, sorry. What was to me extremely interesting was what was found by Palacios. So this kind of stress is a kind of chemical reaction. So during the stress, there is a high electric field, there is a humidity, and the combination between humidity, presence of oxygen, hydrogen, and so on at the surface were making the chemical reaction. And this, in fact, was proved by Palacios. In fact, they found, they did the stress in a very controlled ambient. They did not see any degradation, while the same device stressed in the same way in an ambient with a lot of, let's say, atmosphere, with a lot of water and the humidity, they found this degradation became more and more evident. So this is something I really believe. It was not really the stress, the electrical stress itself that created the damage, but there was the combination of electric field and ambient condition. So with a very good packaging, you may solve this problem. But at the end, this was a very nice exercise. So this was for what was observed in gallium nitride device for RF condition. So let's say in the year 2008, 2014, and they were a Schottky gate, suitable for RF application. Now let's go to what we are more interested today, is the device for power switching application. And yesterday you have seen the presentation from Farid and Peter. They are speaking a lot about P-Gate. So let me show you a little bit about the P-GaN gate. So these are the gallium nitride device. The control gate is not staying over the gallium nitride channel, but there is a P gallium nitride, or Panasonic did the P aluminum gallium nitride. Never mind. It is just a P GaN layer here. What does this P GaN layer here? The P GaN takes the band diagram and push the band diagram up, because the Fermi level, if I have a P GaN P-type material, the Fermi level is closer to the valence band. Without this, these bands will be much lower level, and then this 2DG is much closer to the Fermi level. Then I have the channel. Then I have a normally on device. But if I include the P-GaN here, I push up my band diagram, I take out this 2DG from the Fermi level, I am depleting the channel. So electrostatically, with the P-GaN layer, I am making my normally off device. The problem is that this is a P-GaN, so this is a P-N junction. This is a P-GaN. Underneath here I have the unintentionally doped, who is a little bit less N-type. So this is a P-N junction. So the good of this device is that it is a normally off, because power people want a normally off device, because they say it is intrinsically safe. If some reason I lose the control from my gate because my control gate circuit is a blow up, my device go naturally to the off state. If it is on, maybe I can make a short circuits between VDD and VSS, so they don't like. So the good things of the P-GaN is we do have a normally off device. The bad things is this is a P-N junction. So my gate is not isolated. And this is a problem. But today, this is the best compromise. Oh, this is a typically IV plot that we just to show you. This is my FET structure. This is the ID versus VD at a different VGS. This is the important plot, the drain current in semi-log scale in which you see that at zero drain bias, I do have zero current, almost. This is just noise. And if I put my limits of my threshold voltage defined when the drain current is microamps or 100 or milliamps, you may end up with a threshold voltage of around 1 volt to 2 volts. Then the problem is, if I am having a device like this and I want to use in power condition, I want to be able to open the channel to have as much current as I can. The larger the current is going through my device, the lower the on resistance. So then I wanted to have my normally off device, and I wanted to apply to the gate 10, 20, 30, 50 volts. Who cares? The larger the gate voltage, the larger the current, the better it is. This is not the case, because my device is a PN junction. The larger the gate voltage, the more the device will be in forward condition. So this is the typical IV plot, you see. So in a negative gate bias, no current. For positive, at 1 volt, I start to have some current. And then this goes up, it goes up. Okay, let's try to understand which is the maximum voltage I can apply to my gate in order to have a compromise. I know that if I go too much positive, I will destroy my device sooner or later. But I want as much positive gate bias as possible to have much current as possible. So this is what happens. We did what we call the step stress. So this is the stress voltage at the gate. This is a staircase. You see, we started from 3, 3.5, 4, and so on and so forth. And at each step, we measure the gate current. And you see the gate current remains stable. A certain time, gate current shows some transient in which they decrease, then try to become noisy, and then start to increase too much to the destruction. And this is the IV plot of the diode during the stress. And up to 7 volts, you see, this is the 7-volt staircase. The leakage was a little bit noisy, but not bad. But at 8, 9, 9.5 volts, at this level, the device blow up. Okay. I know that if I give to my device for a short time, let's say some hundred of seconds, 9 volts, the device broke up. It means I have to go lower. How much lower? Depends on the theory. So in order to understand which is the right bias voltage, the maximum bias voltage that I may have, in order to guarantee a reasonable number of years of operating, first of all, we did this what we call the stress test. So the gate current monitored as a function of time at the VGS 8 volt. So 8 volt means that we are in a region where we start to see some degradation, okay? So 8 volts is, let me see here, we are close to see a big jump. Not yet done. And if we look versus time, this is a time to degradation mechanisms. So I start with a very good condition, but after some hours, the leakage started to increase until it breaks up. Okay, then if I know that if I apply 8 volts for a long time, after 6 to 8 hours, I start to see degradation. Okay, I need to know which is my maximum gate bias in order to have 20 years of operation. What do I do? Let me skip this one. What we have to do, we do stress at a different gate bias. You see that at 8 volts, I see a larger degradation on 10 to the 4 second. 8.5, I see at 10 to the 2. 9 volts, 10 to the 1. Then I do this in a statistic way for many devices. I got what I call the log normal distribution. I'm not going to go into detail of this statistical things. It is out of the scope of this course, but if you are interested, let me know. I can address correctly. And then from this variable, I can define a line when, to me, I have a reasonable failure criteria, and I plot this time to failure that I see here in a plot in which I see time to failure versus the gate stress voltage. And I have this point. Then I can extrapolate. Okay, extrapolate. Of course, this is some undetermination because, you know, there is some statistic here, so I have to take care about that. But then I can put the line here. This is 10 to the 9. It means 20 years. And if I extrapolate this point to here, I see that for 20 years operation, I cannot apply more than 6 volts to my device. Okay, 6 volts. In fact, if you go to the market, you take EPC devices or a GaN system device, they are P-GaN, and you will see a very strict constraint about the maximum gate voltage you may apply to your device. The reason is this. So you have a device, you would like to have a much larger gate bias, you can't, because if you apply a larger gate bias, your lifetime will be much less than the 10 or 20 years that they guarantee. The point is, where is it the degradation? Again, we are engineering. We don't want just to qualify the product. To me, just telling you must give a 6 hour to 6 volt to the device to get the 20 years is not something I like to do. I want to know why I must give only 6 hours for having the 20 years and not 8 or 10 volts. And so we wanted to understand the failure mechanisms, the degradation modes and mechanisms. And then this is what we have done, studying the structure. We have seen that very likely most of the problem came at the P-GaN region, who is doped. Then during the high bias, this is bended up a lot. We have a very high electric field in the P-GaN region. And then this very high electric field can damage your structure. So another point is how to solve these issues, and of course this is a material problem. The last 10 minutes of my talk, I wanted to address a little bit the other situation, the other possibility to make a normally off device without going into the P-GaN. Okay, P-GaN today is the best compromise. And as Farid yesterday says, and Peter, I believe is true, at least for the next 5 to 10 years, this will be the device in the market that will provide the best compromise between performance and reliability. But of course, the best solution, like in silicon, the best device is the MOSFET. In gallium nitride, sooner or later, if this technology will have a success to be distributed widely in the market, we will have to go to the MIS-HEMT devices. I know it is difficult. It was difficult even in silicon devices. In the 60s, the problem of the MOSFET has been the interfaces and the oxide. Today, we have a much difficult problem because we don't have only one interface. We have many interfaces. I will show you in a minute. But it will be just a matter of time. Sooner or later, we will solve the problem. We have to. So let's show the other dream, This is the dream of the power device. We wanted to have a GaN devices with a MIS structure, an insulating layer, and with a very high power condition. So first of all, the problem with the insulating layer. If I wanted to make a MIS structure, I have to use an insulating layer. And in general, you know, like silicon nitride is a good insulating layer if you speak about silicon, because silicon has an energy gap of 1.124 eV. But GaN has a wide energy gap, and aluminum gallium nitride, who is on top of the GaN, is even larger, is kind of 4.5. So if you put a silicon nitride on top of aluminum gallium nitride, is that really an insulating layer? The delta EC is pretty small, is 1.3 or less than 1 if you have aluminum gallium nitride. So it is not really an insulating layer. It is good that we have seen all the good property of the in-situ silicon nitride for stabilizing the surface, whatever. This is perfect. But then for having the insulating layer under the gate, I need something else. Today, it looks like the best compromise is aluminum oxide, who is a very wide band gap here, equivalent band gap, with a reasonable good delta EC that avoid the electron to spill over from the GaN or the GaN. And it looks like this is a very good compromise, okay? Then, of course, there are zirconium, there are many other materials. But let's say, in terms of maturity, easy to process, whatever, I believe today this is the good things. But this can change in the future for sure. And then we study a structure that was provided by IMEC with an insulating layer. We try several kinds. For instance, room temperature chemical vapor deposition, silicon nitride, plasma enhanced atomic layer deposition, silicon nitride, or atomic layer deposition, aluminum oxide. Just to do a trial. Let's see what happens. And this was a good trial. We see the gate leakages versus the gate voltages, but also we did a study of the stress versus time. And of course, there's nothing of new here with what we know about the silicon. We have an insulating layer, okay? And this will degrade. The point I wanted to stress you is, remember, you don't have only the insulating layer here, but the AlGaN barrier layer, this is a wide band gap, is another kind of insulating layer. So you will face degradation not only in the insulating layer, but also in the AlGaN barrier layer. This will make things much, much more difficult. We have a lot of interfaces. We have interfaces between the silicon nitride or aluminum oxide and silicon nitride, from that to aluminum gallium nitride, another interface from AlGaN to the GaN channel. So the problem is much, much more complicated. But of course, this is where we have to go. The degradation mechanism is the well-known percolation path degradation mechanism that we know in the oxide. We have, for instance, a silicon oxide. We have the silicon here, the polysilicon gate. And when you stress at high voltage here, you generate a defect. And when the number of defects grow in number so much that you may identify a path connecting your two terminals, then you have what you call percolation path. The leakage grows up, and then your device is kind of gone. Okay, and this is what we have done, for instance, in a device with this kind of structure, MIS-Gate. We have stressed the device at a different gate bias. Note that we were able to go a little bit higher in voltages, 10, 9.5, 9. We did again the log normal distribution. You plot this to the time to break down versus gate voltages. And again here, for having the 20 years, we found the limits of the time that is around 5 to 6 volts. Again, similar procedure to try to get an estimate which is the maximum voltage I can apply to my structure to have enough lifetime. But of course, the maturity of this is far away, well beyond the stabilization. So we need really to work a lot in order to develop this and to have a very good, good material. So degradation related to dielectrics, let me a little bit speed up. Okay, I don't think I am telling much more of new about this. But this maybe is interesting. It was an example of what I have told up to now is related to the material, an ideal structure. But then at the end, you have a very complex structure. And maybe some of your degradation is coming from the geometry, from the architecture of your device. So then this kind of degradation that are less not related to the material itself, but with the device architecture, need to have a different approach. Don't have to change the material or improve the material. You have just to improve your structure of your device. And this is another important point. Not only material, but also processing. So you have to go with the two binary in order to solve and to have the better from these devices. So in this kind of device, these were done during a GaN. We have device from NXP. This is a cross-section of the device. This is the gate with the feed plate. So this is your channel. This small light blue area here is a dielectric between the feed plate that helps to lower the electric field in this area. The gate foot is here. But what we found was that this feed plate at this point here has a peak in the electric field. So we just moved the peak of the electric field from the gate edge to the feed plate edge. So this was indeed a not very good design of the feed plate. We did not lower the electric field. We just moved the electric field peak in another place. So we can do better. So then working either in the design of the feed plate, in the quality and in the kind of the material, they have been able to better design this and to really lower the electric fields. So this is the first generation, this is the second generation, lowering a lot the peak of the electric field. And if I plot here the time to failure versus voltage of the first generation, the second, we were able really just for a fixed, for instance, time to failure, we were able to increase the voltage across the device of 200 volts. So let's say for the same voltage rate, let's say 600, we were able to go from 10 to the 3 to 10 to the 6, so 3 orders of magnitude improve in the lifetime of the device. Okay, I will leave this slide for you for the future. I'm not going to get deep into this. Is ESD failure, electrostatic discharge. It's just more a qualification procedure, just to tell you that in general some over voltages for short time may happen, and then you may drive, you really need to design your circuit in order to guarantee that if you take your system with your hands and you are charged because you are working in a linoleum carpet or whatever floor, and you do not discharge and you destroy your device. All electronic equipment you have in your hand, telephone, computer, any electronic equipment has an ESD protection structure in order to avoid the discharge across the device. Even your USB port of your computer, whenever you connect your USB to your port of your computer, you are injecting charge. If you don't have a ESD protection structure there, your computer port will be dead in few times that you do it. But this is another story. Let me to skip these slides. And what I want to go to the conclusion. Conclusion is, I think that it is no doubt that the gallium nitride device are extremely good device for RF, for power application, and so on. Today, the main limitation factor are the charge trapping and the reliability. To my understanding, if we focus to the 600 volts device class, what Peter yesterday was speaking and Farid also, most of the trapping problem has been under control, okay, are under control. So you may be able to develop and to build devices with negligible current collapse at 600 volts. I'm not telling it is easy task, but you can do. People have done, so it is feasible. What today we need to prove and to do is the reliability. The reliability is still not completely understood. And we don't know very well which are the procedures to establish the reliability of the gallium nitride device. In other words, in silicon, we know everything about the physics, and we know the acceleration law. So I know that if I stress my device at higher voltages and at a higher temperature, I'm able to extrapolate, as we have done before, my lifetime at a lower temperature, lower voltage. In GaN, we are not sure that we know how to qualify our product. At this time, we are applying the qualification procedure that we do for silicon, what we call the JEDEC procedure. So that you have a tot device stressed at a certain voltage, at a certain temperature, and you don't have to see any failure, whatever, blah, blah, blah. But I'm not convinced, I'm not sure that these are enough. Maybe this device, with the defectivity of this device, with the complexity of this device, maybe we need a more complex qualification procedure just to take into account some effect or some physical mechanisms that are not present in the silicon devices. Just to finish in the presentation I will give to you, there are really a number of papers that you can check as a reference if you are interested in reliability. This has been built up by Matteo, so I don't want to cancel them. I hope you will have time to read a few of them. Don't go through all of them. You will be kind of sad after that. You will not want to have any reliability data or information. So thank you very much for your time. I hope that I was able to give you some good messages. I don't believe you will remind the 100 slides, but maybe a few of them, yes. If you have any question, I'm happy to answer. Yes, but you have to come here to speak to the mic, otherwise there is no way to listen your question.
Thank you, Goranzio, for this very enlightening presentation. I have a question about reliability of the P-GaN gate. So from your experience or with your knowledge, if you could choose between a P-GaN gate, which is purely rectangular, or one which has slopes on the edge, which one would you think is better for reliability or for leakage?
I think the answer is easy. What we have to do in any structure to improve the reliability is to lower the origin of the stress. In that case, if I am able to, at the same bias condition, lower the electric field, that means having rounded corner, having some structure, more clever structure of the gate, you lower the electric field, indeed you will improve the reliability. So let's say that for the P-GaN gate, what we have to work to increase the reliability indeed is working on the material for sure, because we need material more stable and more with less defect. But indeed we need to design our gate in an architecture that we lower as much as possible any accelerating mechanisms for the degradation. So you are right.
Thank you.
Thank you. Any other question? Okay, if not, don't thank me again, because I am the speaker and the chair, so I cannot say again this.